So this is our next result as a theorem number 9 on convergent sequences. Here we shall study the geometric sequence x raised to n, and that the convergence of this depends on the value of x. Where it is between 0 and 1, this sequence converges to 0, and it is greater than 1 or between 1 and infinity, it diverges. Now x raised to n will have the terms as x, x square, x cube, etc. So this is the sequence that we have to consider. And the first part is x bit is between 0 and 1. Now we consider this case A. Let 0 is less than x is less than 1. To show this sequence is convergent, we shall first see whether it is increasing or decreasing, or non-decreasing or non-increasing. And we have x raised to n plus 1, which is equal to x into x raised to n. And because x is less than 1, x raised to n is multiplied by less than 1 quantity, the value decreases. That is, this is less than x raised to n. And this means x raised to n plus 1 is n plus 1th term, is less than its nth term. That means the sequence is non-increasing. So therefore, x raised to n is non-increasing. Actually it is decreasing, but we use the word non-increasing. Is a non-increasing sequence. Further, we see x is greater than 0. Therefore, x raised to n is greater than 0. Also, x greater than 0. And therefore, x raised to n is also greater than 0. And that means each term of the sequence is greater than 0. And therefore, the limit is also greater than or equal to 0. And we shall consider limit of x raised to n. Or this shows that the sequence is bounded below. Every term of the sequence is greater than 0 means the sequence is bounded below. Or we can say here n belongs to I. Therefore, x raised to n is bounded below. And thus we have this is a non-increasing sequence which is bounded below, and thus this sequence is convergent. This is theorem 6. A non-increasing sequence which is bounded below is convergent. And we have shown it is convergent. Now we shall show it converges to 0. And let it is convergent means it has a limit, fixed limit. Let limit of x raised to n as n tends to infinity is L. And because the limit of x raised to n is L, we will consider the limit of the sequence x to the power n plus 1, and then we shall see next. Now limit as n tends to infinity of x raised to n plus 1. We shall express this term as limit n tends to infinity x into x raised to n, and the limit is on n. Therefore, this x may be written outside, or this is the theorem, earlier theorem 8. Limit of Csn is equal to C into limit of Sn, and therefore this is x times limit n tends to infinity of x raised to n, and this we have assumed as L. So therefore this is xl, and thus the limit of this sequence x raised to n plus 1 is x times L. But x to the power n plus 1, as n takes value 1 to infinity is a subsequence. It is a subsequence of x raised to n as n takes value 1 to infinity. Now, how it is a subsequence? We have at the start of this chapter we have studied subsequences. The terms of this sequence will be those of that sequence x raised to n. You may see put n is equal to 1. We get the term will start from x square, and here the term starts from x. So therefore, this is a subsequence of x raised to n, and we have a result. If x raised to n is convergent, we have seen, and this is subsequence. If a sequence is convergent, then every subsequence of it is also convergent and converges to the same limit. So since every subsequence of a convergent sequence converges to the same limit. So we must have this sequence x raised to n plus 1 also converges to n. Therefore, this converges to n. But earlier we have seen its limit is xn. Converges to n means it has also the limit as n. Limit n tends to infinity of x raised to n plus 1 is equal to n. And from these two, it is also xn and this is n. We have xn is equal to n. Thus, or if you transfer this term on this side, L into x minus 1 is equal to 0. And you see, x is not 0 because the case is x is greater than 0, x is less than 1. So x is not 1, and therefore x minus 1 is not 0. And this is possible only if L is equal to 0. So this implies L is equal to 0. L is 0 since x is less than 1, x minus 1 is not equal to 0, and therefore we must have L is 0, and L is 0 means what? L is the limit of the sequence. So limit of x raised to n is equal to 0, or this means the sequence x raised to n converges to 0. So this proves the first part, and now we shall consider the second part as b. So in the second part, we have the different case for x. 1 is less than x is less than infinity. And now we shall see what type of sequence is this. Case B, let here 1 less than x less than infinity. Means x is greater than 1. Therefore, x to the power n plus 1 will be again x into x raised to n, and here this is x raised to n is multiplied by a number which is greater than 1, and therefore this quantity will be greater than x raised to n, and thus here we have x raised to n plus 1 is greater than x raised to n, means the n plus 1th term is greater than nth term. The sequence is non-decreasing and means increasing. Therefore, x raised to n, and this is true for n belongs to R, is non-decreasing sequence. The term n plus 1th term is greater than nth term, so it is non-decreasing. Thus, in this case, the sequence is not decreasing, and we shall say the sequence is not bounded above also. And if in sequence is non-decreasing sequence and which is not bounded above, then it diverges to infinity. So further we have to show the sequence diverges to infinity, it is not bounded above. So we shall show that, or we shall prove that is not bounded above. And to prove this result, we shall assume the contrary. Suppose on the contrary, it is bounded above. This is bounded above. Now, what type of sequence it becomes? It is non-decreasing and bounded above. Therefore, x raised to n becomes convergent. This is theorem 4. And therefore, by theorem 4, x raised to n will be convergent. So, this is for your reference by theorem 4. X raised to n is convergent. And now we shall do the same procedure as in part A. Suppose it converges to L. Let limit n tends to infinity of x raised to n is equal to L. And also limit n tends to infinity of x raised to n plus 1 will be limit n tends to infinity of x into x raised to n, which is equal to xn. And again, this is a subsequence of this sequence x raised to n. So therefore, it must converge to the same limit as L. And we must have L is equal to xl as in part A. So, but this is the same reasoning as in part first. Is a subsequence. You know, this is subsequence of this one, because the terms of this sequence are x square, x cube, etc. And what are the terms of this sequence? Starts with x square, x cube, etc. Only one term is difference, and therefore all the terms are there. So this is subsequence of this sequence. X raised to n plus 1 is subsequence of x raised to n, and therefore it must converge to n. If the sequence is convergent to L, then all its subsequences also converge to L. And this means limit of x raised to n plus 1 must also be equal to L. But we have this limit as xl also. And thus, again, we will have xl is equal to L, as in part A. So this implies xl is equal to L. Or if you transfer this term on this side, we will have L into x minus 1 is equal to 0. And now you see what is the value of x? X is again greater than 1. So therefore this is not 0. So this must be 0. So this implies L is equal to 0. Since x is greater than 1, x minus 1 is not equal to 0. Product of two terms is 0, at least one of them is 0. So this implies L is 0. But what is L? L is the limit of this x raised to n, and that is limit of x raised to n is 0. So this is 0. But we have x is greater than 1. So therefore x raised to n is greater than 0. This is given case. And therefore x raised to n is greater than 1 raised to n means 1. And therefore the limit of x raised to n must be greater than or equal to 1. And but what we have here is limit of x raised to n is 0. So this is a contradiction, because the limit we have obtained is 0. Or we may refer this as 1, and this is a contradiction 1. And therefore our supposition is wrong. And that means what we have supposed, the sequence is bounded above. And therefore x raised to n is not bounded above. And thus x raised to n is a non-decreasing sequence which is not bounded above. And by the theorem of 5, this must diverge to infinity. So in theorem 5 we have shown, earlier we have shown it is non-decreasing, and now here we have shown it is not bounded above. And therefore by this theorem x raised to n diverges to infinity. So this proves the theorem. And the meaning of theorem is simple. For every geometric sequence, if the value of x is between 0 and 1, less than 1, 0 less than x is less than 1, then the sequence converges to 0. For example, if you consider this sequence, say 1 by 2 raised to n, as n takes value 1 to infinity, then what about this sequence? So this sequence is convergent, converges to 0 because of this result. X here is half, and half is less than 1. So therefore this converges to 0 or tends to 0. So that is the meaning. Or in other case, if you consider the number greater than 1 means we may consider 3 by 2 raised to n. What about this sequence? Now what is the value of x here? X is equal to 3 by 2, and this is greater than 1, and it falls in the second case. X is greater than 1, therefore the sequence diverges. So this tends to infinity. So these are the two cases, and according to this value of x, we can easily decide whether the sequence converges to 0 or diverges to infinity. So this completes the proof of the theorem. Now we shall consider the next result. Now there are next result for convergent sequences. We have stated earlier also, if limit of Sn is L, then limit n tends to infinity of Sn minus Tn. Sn converges to L, Tn converges to L. Then this limit is L minus L. So this is proved using the earlier result. So this can be written as limit n tends to infinity of Sn plus of minus Tn. And therefore this will be limit of Sn plus limit of minus Tn. And using the earlier theorem also, we have Csn. If C is constant, here minus 1 is constant, that can be written outside the limit. So this is limit of Sn, which is L, and this minus sign can be written separately, and limit of Tn is L. So this is the next result. The detailed proof is written in the notes. Now further, corollary to this result is, if Sn is less than or equal to Tn, then limit of Sn is also less than or equal to limit of Tn. So this is the result. Further, you may assume the same thing, that is Tn tends to m and converges to m and Sn converges to L. Here we will consider this is greater than or equal to Sn. So therefore m minus L is to be considered, and m minus L will be limit of Sn minus limit of Tn, and then because limit of Sn is less than or equal to Tn, this will be less than or equal to 0, and therefore we get the result as the limit of Sn is less than or equal to limit of Tn. So these two are the simple results, you may refer in the notes. Now we consider the next theorem as, if Sn converges to L, then Sn square converges to L square. That is our next theorem. We will prove it as if Sn converges to L, then the sequence Sn square converges to L square. Sn square means square of each term, S1 square, S2 square, etc. So this is another sequence. Now we shall prove it. So actually what we have to do is Sn square converges to L square. So according to definition, so given epsilon greater than 0, we have to prove that there exists n belongs to I, such that the difference of Sn square and L square, absolute difference, Sn square minus L square, is less than epsilon or n greater than or equal to n. So this is the result that we want to do. Then we shall say Sn square converges to L square. But this can be factored as Sn minus L, Sn plus L, less than epsilon, n greater than or equal to n. Or this further can be separated, mod of Sn minus L into mod of Sn plus L. Property of absolute value function is less than epsilon or n greater than or equal to n. So this is the result that we want to prove. Now we consider Sn is convergent, and therefore every convergent sequence is bounded. Since Sn is convergent, it is bounded. So this result we have proved. As earlier theorem, you refer that theorem, Sn is bounded. And therefore there exists, or there is m greater than 0 such that positive real number, such that absolute value of Sn is less than or equal to m for all n belongs to I. Every term of the sequence, mod of Sn means every absolute value term absolute value of every term of the sequence is less than or equal to m, that we will have. And therefore now we will add here L on it, mod of Sn plus L, and this is equal to mod of Sn plus mod or that will be less than or equal. If you separate absolute value, then what we will have is it is less than or equal. This is less than mod Sn plus mod L. And you see, mod Sn is less than or equal to m. So we replace this by m. And this is again less than or equal to m plus l. And this is true for n belongs to I. Every number n, natural number. So this is the result we have. And now again Sn converges to l. So we use this, since also limit n tends to infinity of Sn is equal to l. This is given. So therefore there exists n belongs to I such that this difference Sn minus L, absolute difference, is less than epsilon divided by. Now epsilon we are taking at our choice. So instead of epsilon, we will consider epsilon divided by, here it must be mod L, divided by m plus mod of L. And this is true for n greater than or equal to n. And now we shall suppose this as second and third. And now we combine second and third. Now see, from 2 and 3 we multiply the left sides. So from 2 and 3 we will have, so this will be true for n greater than or equal to n. So this is the condition here for every n, here for greater than or equal to n. So if you consider n greater than or equal to n is in I. So therefore from 2 and 3 for n greater than or equal to l. So what we have is mod of Sn plus l into mod of Sn minus l. Is the relation is strictly less than. Now this is less than m plus mod l, first term, and second absolute value is less than epsilon divided by m plus mod l. And now you see here these two terms divide out and the right side remains as epsilon. That is mod of Sn plus l into mod of Sn minus l is less than epsilon. And this is true for n greater than or equal to n. You remember the conditions. Here n is greater than or equal to n, here n belongs to I. But if you combine it, this condition n should be maximum value, capital N will be there, and this is what is 1. So this is what we want to prove. So we have to prove 1 and we have proved it. So hence 1 is true and this completes the proof. So this proves limit of Sn square is equal to